Hello everyone, my name is Amirhossein Ghaemi. I appreciate everyone attending the talk today. The work I'm going to be talking about today is the classification of COVID-19 and nodules in CD images using deep convolutional neural network. This is joint work I did with my supervisor Dr. Danyali and Mr. Mousavi and his supervisor Dr. Kazemi at the Shiraz University of Technology in the Department of Electrical and Electronics Engineering. This talk is going to consist of four main parts, which are: why should we classify COVID-19 from nodules? What is the importance of this work? And I will review some other works in the literature that can classify just one class of COVID-19 infection and nodule as a lesion from non-lesion. And I'll talk about the proposed deep convolutional neural network architecture and the extensions we proposed in this paper to the ordinary unit encoder architecture. Eventually, we'll get into the results of the medical application we chose to apply this to and study comparative evaluations of the state-of-the-art and proposed method. So, why classification of COVID-19 and nodules? To shorten this into a 15-minute talk, this section is going to try and cover all the background on the importance of diagnosing the COVID and nodule. I'll discuss the background of the COVID-19 and nodule and the importance of correctly diagnosing them from one another. We will also discuss the similarities between these two infections and their impact on the patient's health. So, what are the origins and backgrounds of the COVID-19 infection and nodule? And what is the importance of diagnosing them from each other correctly? In December 2019, in Wuhan, China's first person infected by coronavirus disease 2019, abbreviated COVID-19, was confirmed. And just a few months later, the virus was spreading around the world. COVID-19 is a respiratory illness and is responsible for millions of fatalities. Lung cancer is one of the most drastic and common malignancies, with a 5-year survival rate of barely 13%, and it is leading cause of cancer deaths globally. Lung nodules are the most common early signs of lung cancer. Therefore, the first stage diagnosis of lung cancer has a vital role. Computed tomography image is a crucial tool for observing and analyzing COVID-19 infection and lung nodules. During the COVID-19 pandemic, an excessive amount of lung CT images have been taken, and a certain number of patients identified as a COVID-19 positive may correspondingly have a cancer. So what is the similarity between COVID-19 and nodules, and why is it important to pay attention to it? The tissue infected by COVID-19 has considerable similarity to the symptoms caused by lung cancer, which is known as a nodule. These similarities, such as shape, size, Hounsfield unit values, brings dilemmas for radiologists and may lead them to a mixed diagnosis. This figure illustrates some lesions corresponding to COVID-19 infections and nodules in CT images that show similarities between these two infections. Convolutional neural network is considered one of the most effective algorithms used in image classification applications with excellent results, specifically for biomedical images. So, based on CNN structure, several classification methods have been investigated for automated classifying COVID-19 from non-COVID-19 and nodule from a non-nodule region of interest, abbreviated ROI, in CD images. Some classification networks such as ResNet, Exception, and AlexNet that are studied to distinguish between COVID-19 and non-COVID-19 lesions extracted features from detected regions in CD images and then use transfer learning to optimize the pre-trained CNNs. And in some other CNN-based networks, a genetic algorithm is responsible for feature selection, and the classification is carried out using classifiers, including support vector machine (SVM) and multilayer perceptron (MLP). Well, I'll talk about some CNN-based classification networks that are studied to classify nodule from non-nodule in seed images. Modified AlexNet aims to categorize the input images into three categories: non-nodules, nodules of size less than 3 mm, and nodules of size greater than equal to 3 mm. This classification is accomplished with assistance of pre-trained AlexNet by modifying the last fully connected layer based on the mentioned classes. The second classification approach for line nodules based on the deep residual network is integrated with the ideas of residual learning and migration learning. The model comprises a deep residual network with 50 layers, a global average pooling layer, a fully connected layer, and a classification layer. In this section, I'll discuss the proposed deep convolutional neural network architecture in detail, but first I discuss the pre-processing technique we implement. The original city images carry various noises due to the environmental artifacts. Eliminating noise helps the network to train better and faster. In consequence, the Gaussian filter with 3x3 kernel size is utilized to remove it. In addition, original city images consist of different body organs like the bones, which confuses the model and causes declining accuracy. A patching technique is employed to remove the useless parts of line. 64 by 64 is chosen for the patch size, and each patch contains part of the line, which is labeled as a lesion by radiologists. Subsequently, based on the annotation file provided along the datasets, each patch's label is aligned to 0 or 1, representing that this patch is associated with the COVID-19 infection class or the line nodules class, respectively. The CNN-based method is proposed to surmount the mentioned obstacles associated with line nodule and COVID-19 infection classification in city images. The functioning of CNNs depends on the number of training data. Accordingly to train numerous trainable parameters, data augmentation methods such as zoom in, zoom out, flipping, and rotating in different degrees are applied to the available images to escalate the number of inputs. As we see in this slide, the proposed CNN architecture is inspired by the encoder of unit architecture. It includes 30 layers, 10 of which are convolutional layers and are responsible for extracting the features of their input. Max pooling, dropout, dense, and batch normalization beside convolution layers are the key components of this model that are gathered to extract features effectively. The pre-processed single-channel input images are in the size of 64 by 64 with normalized values between 0 to 1, respectively. Rectifier linear unit ReLU is an activation function for all the convolutional layers. All convolutional filters convolve to their inputs with a kernel size of 3 by 3, and all max pooling is in size of 2 by 2 with 1 pixel as stride, which is obligated to downsample the resolution of its input feature maps. Subsequently, when features are extracted, MLP classifier is placed to separate the features and classify the inputs as COVID-19 infections and nodules, which consists of one dense layer with the size of hidden units of 2048 and 1024, and a dropout layer with a rate of 0.5. The Gaussian error linear unit GLU is chosen as the activation function. Utilization of convolutional features in conjunction with MLP classifier leads to improved classification accuracy. The number of neurons in the final dense layer is defined based on the number of classes, which is set to the 2. The last dense layer's activation function is sigmoid. It is obligated to set the output probability between 0 to 1. The last function helps the network runs efficiently during the backpropagation, allowing the training process. Owing to the aim of our model, which is classifying input images into the two classes, binary cross entropy is implemented as a loss function. The LIDC, IDRI, image collection, and COVID-19 dataset were utilized to generate train data and assess our method's efficiency. In the LIDC IDRI image collection, 1,184 nodule images from 888 randomly chosen patients have included CT scans that were verified by at least 3 out of 4 radiologists, and in the COVID-19 dataset, 1,537 images are extracted from all volumes that contain COVID-19 infections based on the labels. In this slide, I'll discuss how the evaluation of our proposed method works and the setting of our experiments. To evaluate the proposed method, 30% of all data are chosen randomly as the test data. To reduce the probability of overfitting, Adam W is employed as an optimizer with two parameters, including learning rate and weight decay, which both are set to the 0 and 1,000ths. Adam W performs better than Adam in decreasing the training loss with the weight decay or regularization term. All the experiments and models are employed in TensorFlow. The model accelerated and trained on Intel Core i7 9700K with 32 GB of RAM and converged after 30 epochs. In the left figure, right curves that are probability maps depict TPR true positive rate or sensitivity versus FPR false positive rate or 1 minus specificity while applying different threshold levels to predicted outs of our proposed method. Area under the curve or AUC represents the ability of our classification method to distinguish between the COVID-19 infection and nodule class. AUCs of our proposed method with three types of classifiers are depicted in the left figure. According to that, the MLP classifier outperforms other classifiers with an AUC of 0.9963. To clarify the effectiveness of our proposed method, the outputs from the test data are gathered into the confusion matrix. It represents only 18 images out of 817 images classified incorrectly. This slide represents several examples of predicted lesions using our proposed classification method. As depicted in A, the true label is a line nodule. In B, the true label is COVID-19 infection, and all the patches except the last one of each row are predicted correctly. In this slide, Table 1 and 2 provide comparative evaluations of the state-of-the-art methods that categorize just one class of COVID-19 infection and nodule as a lesion from non-lesion area. And as illustrated in Table 3, our proposed method classifying input images into COVID-19 infections and line nodules, all the main classification metrics of our proposed method, including accuracy, sensitivity, and specificity, shows promising results compared to the state-of-the-art frameworks stated above. By employing the Gaussian filter to reduce the noise of input patches and using augmentation techniques to increase the number of training data, the capabilities of our proposed CNN-based method, along with the MLP classifier provided by CNN features, are improved. And compared to the other state-of-the-art single-class classification methods, our proposed method has shown decent performance in classifying COVID-19 infections from nodules, with an accuracy of 97.80%. Eventually, the prominent features of our proposed method include the following: decreases the training runtime by reducing the parameters and being patch-based, avoiding the overfitting by implementing dropout layer and utilizing augmentation techniques and Adam W optimizer, attain the precise results with MLP classifier that performs through the entire network during training. Thanks for your time and attention.